Hello guys, welcome back to the channel. Today we're going to talk about isolation forest anomaly detection using random partitioning. Isolation forest is mainly used for finding out anomalies in our dataset. So let's go for it. And most anomaly detection algorithms we use today try to learn what normal data looks like first. Isolation forest, however, takes a complete different approach. It directly isolates anomalies instead. In this presentation, I'll walk you to the intuition behind the algorithm and how it works step by step, the mathematical foundation, and finally a complete working example to prove it. Well, s- start. So we'll begin with a quick overview of what anomaly detection and then move into isolation forest. Understand the core intuition, go through the algorithm, explore the math, and finally validate the everything using a real example. So, anomaly detection. Anomaly detection is a process of identifying data points that significantly deviate from expected patterns. There are mainly three types: point anomalies, a single unusual value; contextual anomalies, unusual in a specific content; collective anomalies, unusual patterns in a group. This concept is widely used by real-world applications such as fraud detection, network security, and medical diagnosis, and sensor monitoring, and etc. Many more. So let's introduce ourselves to isolation forest. So forest is a unsupervised machine learning algorithm introduced in 2008. Instead of modeling normal behavior like traditional methods, it isolates anomalies using random partitioning. It is highly efficient with linear time complexity, low memory usage, and it works well even with high dimensional data. We can have multiple attributes with it. So let's talk about our core intuition. So the entire algorithm is based on one key idea. Anomalies are few and different, so they are easy to isolate. Imagine randomly cutting a space down into a smaller regions, and like slicing a pizza. If we take it as a pizza and we can slice it and isolate the pieces we want out. A point is far away from others can be isolated with just one or two cuts or few cuts. But a point inside a dense cluster requires many cuts to isolate. This leads to a core rule. 1. Short path length means anomaly, long path length means normal. So let's know how to build an isolation tree. Each isolation tree is built using completely random decisions. First we take a random subset of the data, then we randomly select a feature. Next, we choose a random split value within the feature's range. The data is split into two parts, and this process repeats recursively. We find and we stop when a point is isolated or when we reach a predefined height limit, and so that we cannot go split it any further else. And importantly, there is no optimization here. Everything is random. We'll just split everything in random order until we find the leaf node or for the last height building a forest. Instead of relying on a single tree, we build multiple trees, typically around 100, 150, 200. That's that time. This collection of trees is called isolation forest, just like random forest where we use decision tree and we collectively use an example methods to make a decision out of the multiple decision trees. So to evaluate a data point, we pass it through all trees and measure how deep it travels before it isolates. Then we compute the average path length across all trees. Let's talk about mathematical foundation and formulas we use to find the anomaly score, which helps us define how much uh, how much passes it takes to find the or slice the point out. Let's formalize this idea. The path length determined by h of x is the number of edges a point travels in a tree before it is isolated. We compute the average path length across all trees called E h of x. Then we normalize this using a factor C of n where it represents the expected path length in a random tree. Finally, we compute the anomaly score, which is Sxn is equal to 2 power minus EH of x divided by C power Cn. So if a score is close to 1, the point is likely to be anomaly, and if it is around 0.5, it is considered as normal. And if it is 0, it's actually considered very normal, and it has more occurring points around them. Let's take an example data set here. Let's apply this to a small data set of let 10 points. Most of points are clustered together, but points A and B are placed far away. These are our expected anomalies. So when we build these trees, something interesting happens. Points A and B get isolated very quickly, often at the depth of 1 or 2. In contrast, normal points require multiple levels of splits to reach the depths of like 4, 5, and 6. This contrast normal points out that multiple slits and required to point out normal and less to point out the anomaly first. This clearly shows that anomalies are separated much faster than normal data. And let's look at path length summary with the dataset we used earlier. Look at all the averages. Normal points have path lengths of about 1.33 and a point B around 1.67. The difference is what drives the anomaly detection. Let's normalize the factor. We compute the normalization factor Cn for n is equal to 10, which comes out approximately with 3.75. We can round it up, and this helps us standardize the anomaly score. Well, this is the formula we use to find the anomaly score. And let's take with the example of A. Point A gets a score of 0.7820 anomaly score, and point B gets a score of 0.73. So normal points are well above or around 0.5. So clearly anomalies have higher scores. So let's have a final classification of things. By setting a threshold, for example 0.6, we classify A and B as anomalies and all other points lesser than 0.6 as normal and very normal. And the algorithm successfully identifies the outliers. If a node contains uh, let's say the node contains multiple points at a stopping depth, we adjust the path length using C of size to estimate further splitting. This ensures accurate scoring and helps us in finding out anomalies faster. So let's see what are the hyperparameters and the complexity we have in this performance. So in practice, we use around 100 trees and a sample size of 256. This algorithm runs in a linear time, makes it highly scalable for different bigger size of data sets. So let's talk about advantages of having using a isolation forest. Forest is fast and mostly efficient and works well with high dimensional data. However, it uses axis parallel splits, which can struggle with certain patterns, and it may miss clustered anomalies. So let's look at applications and variants. It's widely used in fraud detection, cybersecurity, IoT, healthcare, data quality, and noticeable variants. Extend score. Okay. Let's summarize what we learned here. To summarize, isolation forest detects anomalies by isolating them rather than modeling normal data. Anomalies have a shorter path lengths, which translates to higher anomaly scores. With the formula we use, with the formula in here, s of xn into e is equal to 2 power e power minus e hx divided by c power n, ranging between 0 to 1. It makes the algorithm very powerful and efficient solution for real world anomaly detection problems. And thank you. That's all. Here are the references I used to make the presentation. So thank you. I'm very happy to take any questions in the comments. So thank you.